I'm Tim Norday, and I'm going to be explaining to you how I calculated the critical exponents for butane, as you can see right there. So first thing to note, here are the three relationships to be explained in a second, but the critical values for butane for temperature is 425.125 Kelvin, for pressure in bars it's 37.96, and for critical volume it's 0.2549 liters over moles. So the first relationship, the temperature-dependent critical relationship, is that the change in volume is proportional to the change in temperature raised to beta, the absolute value of the change in temperature. For the pressure-dependent critical equation, or relationship, it's the absolute value of the change in pressure is proportional to the change in volume raised to delta. And then the isothermal compressibility relationship is that kappa, or isothermal compressibility, is proportional to the absolute value of the change in temperature raised to the negative gamma. And one thing you have to realize is that in front of each relationship is a constant that we don't know, and we can't do anything for it. It's represented by C in each of these equations. And all it means is that we cannot equate each side of these relationships to each other, and it makes our finding and isolating the exponent more difficult. So in order to isolate each exponent, we just have to linearize it some way, and we do that with natural logs. And we can bring each exponent down following logarithmic rules, and we end up with each of these equations for each exponent. As you can see, as gamma is negative, it just switches the placement.
So pulling data from the NIST site and plotting the natural log of change in volume and the natural log of change in temperature for points near the critical point, a graph is produced with a line, and the slope of that line is our exponent beta, as you can see. So as mentioned before with gamma, finding it and isolating it is a little bit more difficult because it's based off of kappa, which is a function of 1 over volume times the change in volume over the change in pressure. First, we have to find the change in volume over the change in pressure, and that is found by finding data under saturated temperature values at the NIST site near the critical temperature and plotting them against each other. The fit line of those data produces, we can take the derivative of that fit polynomial line, and that derivative is equal to the change in volume over the change in pressure. And each x value in that derivative is just the pressure at each point we desire. So we take that kappa value for each point, and we plot the natural log of that versus the natural log of temperature. And that resulting graph is the graph of gamma, where the slope 0.2113, negative 0.2113 is equal to negative gamma, as gamma was listed as a negative in its relationship equation. So there you have it, gamma is 0.2113. The exponent delta was found the same way as the others, except its data from the NIST site was taken at an isothermal temperature, the critical temperature 425.125 Kelvin. To find it, we just took the natural log of the change in volume and the natural log of the change in pressure and put them in for each point, the natural log of volume in the y-axis and natural log of pressure in the x-axis, plotted that graph. The resulting relationship, or fit line, a linear line, produced the exponent delta as a slope. As you can see in the graph, 0.0041 is delta. So, for this relationship, kappa is 1 over volume times the change in volume or change in pressure, where each change in pressure and change in volume is determined from each respective point taken to the data. And the final values for each exponent are displayed here in respect to the literature given values. And as you can see, pretty off, mainly due to not the lack of data, but the unsatisfactory type of data.